Good morning to everyone. Again, I welcome you all for another presentation. In this presentation, we will continue the previous problem which we have discussed in last presentation. So, by the way, this is the lecture number 47. And in previous presentation, we have seen this particular mechanical translational system. Okay, so for which we have drawn the electrical equivalent diagram using force voltage analogy in previous presentation. So in this particular presentation, we will see the electrical equivalent of the same block diagram using force current analogy. Force current analogy. Here, so this is what the example actually. So you can consider this is the continuation of the same problem, previous problem. Okay, so here the solution part I am writing for you, this solution part. Okay, so for any given mechanical, first of all you need to write the differential equations. Okay, so as we have two blocks in this, m1 and then m2 with respect to corresponding displacements y1 and y2, therefore you will have two differential equations. So I already explained you that the number of blocks equal to the number of differential equations. Therefore, with respect the differential equation, you can write like this: the differential equations, because the same equations what we have seen in previous presentation, but for your quick and ready reference I am writing the same equations again here. The differential equation with respect to m1, you can write like this: with respect to m1, with respect to m1. So how? Therefore, this is the applied force f of t. K1 is the spring constant associated with m1. F or B sometimes can also be given as B. F is the frictional coefficient. Y1 is the displacement. K2 is the common element. Therefore, some opposing force will be there always with respect to m1. Therefore, the differential equation starting from this m1 block, you can write like this. This is m1 into d square y1 by dt square. With okay, starting from this m1, then k1 into y1 plus f, you can write, or b, whatever you can write, no problem. In the problem f is given, therefore we follow the same notation. It is d y1 by dt, because for f frictional coefficient the first derivative of displacement will come, and then the common k2, common element k2 into what is that, y1 minus y2, y1 minus y2 is equal to your f of t, your f of t. Call it as equation number 1. This is the differential equation with respect to m1. Similarly, you write the differential equation with respect to m2. Similarly, the differential equation with respect to m2. So what we will have, only k2 will be there, and the force with respect to m2 is there. That is nothing but your m2 into d square y2 by dt square plus it is k2 into y2 minus y1 here, y2 minus y1 equal to 0. Clear? This is your equation number 2. Clear? So these are the differential equations governing to this particular mechanical block diagram. Clear? Now, in these expressions, I think now I will erase this particular block diagram. It is not required now. It is not required now. Now what we will write now? So in these two equations, we will write the corresponding electrical equivalent parameters using your force voltage analogy, force current analogy, sorry. Now you can write that using force current, using force current analogy. Okay, equation 1 becomes, your equation 1 becomes how? So from equation 1 analogy, equation 1 becomes as follows. Okay, so what is m1? M1 becomes as your c1. Clear? So what is d square? Y1 by dt square. So it is force current. Therefore, force current, I already explained you that. So it is current equivalent. Current is equal to V by R. This is the form you must have. Means what is the current flowing through each element? So here remember that your mass element will be equivalent to your electrical parameter C. K1 is equal to equivalent to your L actually inductance, and obviously this is nothing but your R, nothing but here you can write 1 by L, otherwise this will be 1 by L, this is nothing but 1 by R, that's all. Again it is 1 by L2 like that, and force becomes as current. Therefore if you write the same, so then it becomes nothing but it is C1 into dV1 by dt. Okay, dV1 by dt plus what is that? 1 by L1. This is K1 1 by L1. So what will come actually? Integral over V1 dt, and that is plus 1 by R1. Is it not? F means only B or F. Therefore R1 is not required, only okay 1 by R into V1. 3 elements, and similarly the common element is there. Common element is there. That is nothing but 1 by L2 plus 1 by L2 into integral of, you can write V1 minus V2 dt. This is equal to your force actually converted to I of t. This is equation number 4, let us say. Equation number 4. Clear? I already explained you in force current analogy. Your M becomes C, K becomes 1 by L. Okay, so and F becomes 1 by R. Therefore, in each element, capacitance, inductance, and resistance, across these elements, what is the current flowing through that? Those are the equivalent actually. This is the voltage flowing through the capacitor, or the voltage across the capacitor. This is the voltage across, current. Current, it's not voltage, it is current. Current across the capacitor, current across the inductor, current across the resistor. That's what actually, that's what. As it is a common, therefore V1 minus V2 will come and equal to I of t. And similarly from equation 2. So this is from equation 1, and from equation 2, using your force current analogy, what is M2? M2 is nothing but again your C2. It is dV2 by dt plus 1 by L2. K2 is nothing but your 1 by L2 integral over, what is this? V2 minus V1 here into dt equal to 0. This is what equation number 5. 1, 2, is it 4 or what? This is 1, 2, you can call it as 3. You can call it as equation number 3, not 4. This you can call as equation number 3, and this is equation number 4. That's all. Your problem is over now. Now, these are what? The equivalent electrical equations for these two differential equations, mechanical equations. Now, by using 3 and 4, you draw the equivalent electrical circuit. Okay? By using equation 3 and 4, the electrical equivalent using your force current analogy. In force current analogy, normally, so what we will have? I is equal to V by R. So, here, two nodal voltages will come, V1 and then V2. Let us say V1, okay, you can represent like this. Say for example, you can write somewhere V1 and something V2. Two nodal voltages will be there. At particular node V1, so corresponding to equation 3, C1 you write, means C1 for C1. What it is? 1 by L1. Parallelly, you can draw inductance also like this. This is what your L1, and then what else is there? R is there. Therefore, draw this like this. This is resistance. Okay. Then what is the common? 1 by L2, V1 minus V2. So between V1 and V2, okay, for these two, V1, V2, L2 is common. Therefore, here it is 1 by L2. But in your representation, you must show like this only, L2 only. But in expression, we will write 1 by L2. But whereas in representation of electrical, you can write L2, V1 minus V2 is equal to I of t. nothing but here for this particular your circuit will be like this. You can connect like this. This is what your I of t according to your equation number 3 with respect to your m1 otherwise. This is the expression. Similarly, coming to the v2 means second expression. At v2, consider the second, fourth expression. Again here c2 into, c2 is nothing but you can draw. So all the element you should represent in parallel, c2. Then 1 by L2 is already there, v2 minus v1, that's it. That's it, you have only one thing. So you can represent ground or something like this. Is the electrical equivalent using your force current analogy. This is V2, this is V1. So compare with these electrical equations with respect to the same actually means that this I of t, okay, I of t flows like this. Okay, if you equate your KVL or KCL, whatever it is, so it will be same actually. It will be same. Clear? Clear. So this is what the electrical equivalent circuit basically. Okay. Electrical equivalent circuit. I think the common element what they have shown actually in mechanical. In mechanical you have K1 to no. Clear? Like this. This is what your electrical equivalent using your force current analogy. This is the continuation part of our previous presentation. So I think we will finish off here, and I think next we will see similar kind of things for mechanical rotational systems. So far we have seen the mechanical translational system. So for the given mechanical translation systems, we have seen the corresponding or equivalent electrical using force voltage as well as force current analogies. So in the same way, if the mechanical rotational system is given, how this rotational system can be converted into electrical equivalent circuits using your force voltage and force current analogy. So remember that your the conversion part in mechanical rotational to electrical same as your mechanical translational system. Only one difference is that instead of M you will have J, moment of inertia J. That's it. That's it. And one more thing is, instead of your displacements, say for example we are considering the displacements as x and x1 or y1 y2 like that, no, whereas in rotational systems you will be we will consider that displacement as theta. So in mechanical translational only two difference will be there. Your M mechanical translational, in mechanical translational we have mass element M, whereas in rotational we will have moment of inertia J. And in this either x or y we are considering the displacement, whereas you consider theta, angular displacement. That's it. So by using this simple this thing, the rest part 100% is same whatever the electrical equivalent comes, same as translational system, nothing new actually. Only the parameter, wherever M comes we will convert J, wherever these comes we will convert theta. And in the subsequently using the force voltage, so using force voltage, so this J can be converted as your voltage, means it is okay. So one more thing is in mechanical we have force actually, whereas in mechanical you have applied force F of t, whereas you have torque actually. This is very important. Your mechanical block diagram you will have force actually, whereas in rotational system you will have torque. Therefore that's why it is called torque voltage analogy. Similarly torque current analogy. Okay, torque to voltage conversion, torque to current. Similarly, so in torque to voltage, your torque will be converted as voltage, and your M is same as your J theta will be same as what we have done in mechanical translational with respect to both voltage part as well as current part. Similar. We will see the few examples on the rotational also in our subsequent presentations. Okay, so I will finish off this presentation here and we will continue in the next presentation. Thank you. Have a beautiful day.